And on to beta decay. We're gonna do these alphabetically as the Greeks did. So the question is, what is beta decay? And it turns out that beta decay is electrons flying out of your nucleus. What? What are electrons doing in my nucleus? Let's first celebrate. Yay, electrons are really fun. Secondly, we ask the question, how the heck did electrons get up in my nucleus? And the answer is neutrons. Neutrons that you thought you trusted, they are unstable. They do not like existing. A neutron is unstable. I don't know if you heard me say that, but a neutron itself is actually unstable. So, what you've got is a neutron that has 0 protons in it. Yep. And 1 atomic mass number turns into, you want to guess what it turns into? Well, what's the charge of a neutron? I guess 0. So it has to turn into something that has a net charge of 0. So watch this. You're going to actually get a proton and an electron. And guess which one stays in your nucleus? It's the big fat guy. This guy, being 2,000 times more massive than that guy, stays around while this guy shoots out. So the neutron in the nucleus converts to a proton in the nucleus and drops off an electron that has a ton of kinetic energy as a result, because the mass of these two guys is slightly less than the mass of that guy right there. And that extra mass turns into energy. I guess delta M is going to be E over C square. Wow. MC square is E. Yeah, wow, that's cool. So you got this is let's get a daddy. Here's a daddy. X, the daddy, and it's got that many protons and that many protons plus neutrons, and it's daddy, and it's going to decay into the daughter, and the daughter is some other element. Oh, again, we've got the switching element thing. Now, does it have the same number of protons? It can't, because it's a new element, right? So what do we have to do? What happens to the numbers of protons if one of your neutrons turns into a proton? Well, shoot, you're gonna have more protons. What? This is weird. It's like it's gaining, it's moving up on the periodic table. That's always surprised me. But what happens to the total number of protons plus neutrons? If you turn one neutron into a proton, do you think A notices? No way. Plus, you get an electron flying off. Now that's cool, but it could also be, wait a second. It could also be an anti-electron, like a positron. So when I told you the beta decay was electrons, I have to add that beta decay is electrons or positrons. A positron is just an electron that's going backwards in time, so we don't have to worry about that too much. We're just going to change this equation, like I had that going to that. I'm just going to change it so instead it will be 1 neutron going into, oh dear. Nope, I don't want to talk about that. What I am going to talk about is that the daddy, in the case of a positron coming out, will be all like this, and it will turn into some different element where it's got the same A, but it's got one fewer proton, because I guess whoa, it's like a proton captured an electron, and that's sometimes called electron capture. Because the opposite of spitting out an electron is capturing an electron. And the opposite of spitting out an electron is spitting out an anti-electron. And capturing an electron is the same thing as spitting out an anti-electron. Because having an anti-electron is exactly like not having a real electron. Sorry, I mean, that's a mess. I'm sorry to bother you. So I'm going to get this daughter plus a positron. That's the symbol for a positron. That's the symbol for an electron. This is the opposite of that. Now, this system right here, what am I trying to say? This guy right here is called beta minus decay. And when it's doing stuff like this, we've got what's called beta plus decay. All right, okay. So one example is, no, I'm not gonna do the energy right now. Here's the thing. When stuff decays like this, I've got something with Z and A going to something with Z plus 1 and A, or with this beta minus, right? And then I've got something, I could also have the possibility of going to Z minus 1, and this would be electron release, and this would be electron capture. This is called beta plus decay. Energy has to be conserved, right? And momentum has to be conserved. So that would predict that in the case of, oh, sorry, this has got an electron coming off here, and this has got a positron coming off here. That would predict that each of these electrons coming off of a certain atom would always have the exact same energy. But there's a huge problem. Do you see why it would have to have the same energy? Because it's always the same reaction. It's always an electron getting spit out, and so it's always got its momentum and energy have to be conserved. Then we'll always have the same energy as the electron. But the problem is, they don't. So here's what you get. If you graph the following function, you graph how much kinetic energy that electron has. But you're graphing what you're graphing is, you're graphing really the probability of electron having some, this is the largest axis I've ever written, having some kinetic energy when emitted. It's going into my graph even. When emitted via beta minus decay. There, that's the largest axis I've ever written. And the probability of an electron having some kinetic energy when emitted by beta decay, it's got some probability of having no kinetic energy at all. And it's got some probability of having some kinetic energy there, and it's got some, look at that. It stops right here. There is no probability of having electrons come out with a kinetic energy like this. But it turns out that this is the kinetic energy that would be predicted by momentum and energy, well, I'm going to write it in more general form, energy conservation. This is a huge problem. Momentum and energy conservation are kind of like sacred things in physics. We do not want to allow those things to go unbroken for a very long time. Like, what I mean is, every electron that comes out does not have enough kinetic energy. Not only that, but they don't all have the same energy. Some of them have way too little energy, and some of them have almost enough energy, but energy is missing here. And so everybody in physics got pissed off. Not only is energy missing, but momentum is not conserved, and freaking angular momentum is not conserved. You've got no momentum conservation, you've got no angular momentum conservation, so really you've got pretty much nothing. Wolfgang Pauli was very angry about this. And he said there must be something else going on. When you have something that is emitting an electron, he said, what if something else also shoots off at some random direction? What if this other thing, this mystery blob, oh, it's probably going to be really small, right? Because we haven't seen it. It's extremely small, and it can come off in a random direction, which would explain the strange range of kinetic energies, because if it's not coming off if it's going off in the same direction versus going the opposite direction, then momentum conservation will give us a lot of freedom with the angle of the momentum to give us a whole bunch of different kinetic energy relationships. But he also says, we know that this thing can't be detected very easily. Well, we've never detected it, we just see its evidence. And we know, therefore, it can't be charged, and it must be really tiny, because the energy that's not adding up is, wow, it was a big chunk of energy, so that means this particle that's coming out must be incredibly small, because it's going really fast. And Fermi was reading what Wolfgang Pauli said, and Fermi, being Italian, said, hey, I've got just the word for it. In Italian, we like to call things that are small and neutral neutrinos, because it means neutrino. It means small neutral thing in Italian. So, okay, the neutrino was born by this observation right here. Here's the thing about neutrinos. We have to now change our equation for beta decay. Here's beta minus decay. It's a neutron going into a proton that has one proton and one proton or neutron, right? And then an electron and a neutrino. And I'll talk about that line later on. But I want to tell you a little about neutrinos. Neutrinos, until 1998 or 7 or something, we didn't even know they had mass. They are super small and really neutral. There's a perfect name for them, right? I'm glad that you guys speak Italian now. Get this. Out of every 200 million neutrinos that pass through the entire planet Earth, one of them will interact during its time passing through Earth. I'm not talking about you needing a sheet of paper to stop a neutrino. You need several planets thick of lead to stop a neutrino. Dang, it's hard to find these suckers. Every 200 million, one of them interacts with our planet. Wow, and until 1998, we didn't even know they had mass. So beta decay is now a neutron going into a proton and an electron, and also an anti-electron neutrino. That's what that means there, that is anti. And that just means it's going backwards in time. What, you want a nuclear physics class? This is an intro physics class. Go watch somebody else's videos. Goodbye. Stays around while this guy shoots out. So the neutron in the nucleus converts to a proton in the nucleus and drops off an electron that has a ton of kinetic energy as a result, because the mass of these two guys is slightly less than the mass of that guy right there, and that extra mass is unstable. I don't know if you heard me say that, but a neutron itself is actually unstable. So what you've got is a neutron that has 0 protons in it. Yep. And 1 atomic mass number turns into, you want to guess what it turns into? Well, what's the charge of a neutron? I guess 0. So it has to turn into something that has a net charge of 0. So watch this. You're going to actually get a proton and an electron. And guess which one stays in your nucleus? It's the big fat guy. This guy being 2,000 times more massive than that guy. Hey, electrons are really fun. Secondly, we asked the question, how the heck did electrons get up in my nucleus? And the answer is neutrons. Neutrons that you thought you trusted, they are unstable. They do not like existing. A neutron. And on to beta decay. We're going to do these alphabetically as the Greeks did. So the question is, what is beta decay? And it turns out that beta decay is electrons flying out of your nucleus. What? What are electrons doing in my nucleus? Let's first celebrate. Yeah.